A supernova is one of the most dramatic and violent events in the universe, a massive explosion that marks the death of a star. The moment it happens, the energy released outshines entire galaxies, obliterating everything within its reach. But how does a supernova explode? What causes a star to go from a shining beacon in the sky to an unfathomable cosmic catastrophe? To understand this, we first need to delve into the life of a star. Stars are not just static bodies of light, they are massive nuclear reactors, continuously fusing lighter elements like hydrogen into heavier ones. This fusion process is what powers the star, generating heat and light that streams across the cosmos. The energy produced by fusion also creates an outward pressure that counteracts the immense force of gravity pulling inward on the star's mass. For most of a star's life, this balance keeps it stable. But all stars eventually run out of fuel, and that is when things begin to take a turn for the worst. The death of a massive star type II Supernova. In stars much larger than our Sun, at least 8 times the Sun's mass, the end comes with a spectacular death. These massive stars burn through their nuclear fuel at an incredible rate. Over millions or even billions of years, the core fuses hydrogen into helium, and then, when the hydrogen is depleted, it starts fusing helium into carbon, oxygen, and heavier elements like neon, magnesium, and silicon. Each new element created in the core is progressively harder to fuse, requiring more extreme temperatures and pressures. The star's outer layers expand, and the star swells into a red supergiant. But deep within the core, something sinister is brewing. Eventually, the star's core will attempt to fuse iron, the heaviest element that can be formed through fusion within the star itself. Iron is a different beast from the lighter elements. Instead of releasing energy when fused, iron consumes it. And this changes everything. As the core becomes increasingly composed of iron, it no longer produces enough energy to counteract the star's own gravity. The balance that kept the star stable for millions of years suddenly collapses. Gravity wins, and the core starts to shrink, compressing under its own immense weight. In a matter of seconds, the core contracts from the size of Earth to just a few miles across. The temperature soars to billions of degrees, and the pressure inside the core reaches unimaginable levels. This core collapse is the first step in the supernova explosion. As the core implodes, the outer layers of the star come crashing inward, accelerating towards the now incredibly dense core at speeds of up to 70,000 kilometers per second. But they don't simply stop when they hit the core. No, what happens next is far more violent. The core rebounds. At the center of the collapsing star, the core becomes so dense that protons and electrons are squeezed together, forming neutrons. In an instant, the core transforms into a neutron star, a compact, super-dense remnant only about 20 kilometers wide, but with a mass up to twice that of the Sun. The neutrons resist further compression, and the imploding material slams into this incompressible core, causing a powerful rebound effect. This rebound sends a shockwave blasting outward, smashing through the collapsing layers of the star. But even this is not enough to cause the explosion, at least not yet. The shockwave begins to stall as it loses energy plowing through the star's dense layers. For the supernova to fully detonate, something else is needed: neutrinos. Neutrinos, the silent killers. In the milliseconds following the core collapse, an immense flood of neutrinos, subatomic particles with almost no mass, pours out of the core. These neutrinos are the real game changers. Despite their ghost-like ability to pass through almost any matter undetected, the sheer number of them, trillions upon trillions, begins to heat the star's outer layers. This sudden energy boost re-energizes the shockwave, allowing it to continue its deadly journey outward. The shockwave accelerates through the star's outer layers, tearing them apart with unimaginable force. The outer layers are blasted into space, creating a massive expanding cloud of debris that we can see as a supernova remnant. The star's core, now a neutron star or black hole, is left behind, a relic of the cosmic explosion. The birth of heavy elements. As the star explodes, temperatures reach more than 100 billion degrees Celsius. This is where some of the heaviest elements in the universe are born. The intense heat and pressure during the explosion force atomic nuclei to slam together, creating elements heavier than iron, like gold, silver, uranium, and platinum. Every atom of gold in your jewelry was likely forged in the heart of a supernova billions of years ago. This process, known as nucleosynthesis, is responsible for scattering these heavy elements across the universe, seeding future generations of stars and planets. In a way, supernovae are the universe's ultimate recyclers. Without them, elements like carbon, oxygen, and nitrogen, the building blocks of life, would never have been created. The aftermath: supernova remnants. After the initial explosion, the debris from the star's outer layers continues to expand outward at high speeds, creating what is known as a supernova remnant. These remnants can be seen across the sky as glowing clouds of gas and dust, slowly cooling over thousands of years. Some of the most famous supernova remnants include the Crab Nebula, the Veil Nebula, and the remnants of the famous 1987A supernova in the Large Magellanic Cloud. At the heart of the remnant, the star's core may remain as a neutron star, a dense ball of neutrons spinning rapidly, often emitting beams of radiation as a pulsar. If the star was massive enough, the core could collapse into a black hole, an object so dense that not even light can escape its gravity. The black hole would sit in the center of the remnant, slowly consuming any nearby material. Type II Supernova, a different path. While Type II supernovae result from the death of massive stars, there's another kind of supernova, Type Ia, that happens in a very different way. Type Ia supernovae occur in binary star systems, where two stars orbit each other. One of the stars is a white dwarf, the remnant of a smaller star that has already gone through its life cycle. In this scenario, the white dwarf slowly pulls material from its companion star. Over time, the white dwarf grows more massive until it reaches a critical point, the Chandrasekhar limit, about 1.4 times the mass of the Sun. Once the white dwarf exceeds this limit, it can no longer support itself, and it undergoes a runaway fusion reaction. The entire star is obliterated in a thermonuclear explosion, leaving behind no core, just a rapidly expanding cloud of gas. Type Ia supernovae are incredibly important in astronomy because they all explode with a consistent brightness, making them useful as standard candles to measure vast distances across the universe. The violent beauty of a supernova. A supernova is a paradoxical event, both a force of destruction and creation. It obliterates the star that gave it life, but in doing so, it seeds the universe with the heavy elements needed for future stars, planets, and even life itself. The explosion unleashes more energy in a few seconds than the Sun will produce in its entire 10 billion-year lifespan. Yet, for all their violence, supernovae are also relatively rare. In a galaxy like the Milky Way, which contains hundreds of billions of stars, only a few supernovae occur every century. When they do, however, they leave an indelible mark on the cosmos. For us on Earth, the explosion of a supernova would be catastrophic if it happened close enough, within 30 light-years or so. Fortunately, the nearest stars capable of going supernova are much farther away. Still, the mere thought of such a colossal explosion is enough to remind us of how small we are in the grand scale of the universe. The next time you look up at the night sky and see the twinkling lights of distant stars, remember that one day, some of those stars will explode in a violent supernova, continuing the cycle of destruction and creation that has shaped the universe for billions of years. In the end, every star must die. But in its death, a new beginning is forged, scattering the seeds of future worlds across the cosmos.